Right, so in a few minutes, the finals of the at-home league will start. So the first league of at-home, the SSPL league, that is starting its finals. So we are starting a round in 5 minutes. And there are two teams that are prepared for the finals. So one is the SKUBA team, who is currently ranked second, and the SinfonIA team, which is currently ranked first. The teams can show a free performance, which should be also quite understandable and quite sophisticated. The team will also explain what they are showing, and there is an external and an internal jury that is evaluating the test.
Dames en heren, over 5 minuten beginnen wij hier bij de at-home arena's met onze finales. Als eerste hebben wij het sociale standaard platform, waar onze 2 finalisten vrij zijn om een jury onder de indruk te maken met wat zij allemaal kunnen.
RoboCup. RoboCup. RoboCup at home finals are about to begin for SSPL. Testing. Can you hear? Can you hear us? Can you hear? No? Testing.
Test.
One more time. We're about to begin the RoboCup at Home SSPL Finals. We've got external jury who will judge. We've got Eccles Chen, co-founder of Unitree Robotics, Chayoy Lee from Booster Robotics, and Emil Kruger from United Robotics Group. The finals for RoboCup at Home are a demonstration of their best abilities, judged by the panel of externals and the executive committee members. They get 10 minutes of showing off their abilities, giving us a demonstration, and then there's going to be a 5-minute question period after that. The first team up is Team SKUBA. Team SKUBA's robot is just turning on, has hardware problems.
Good morning everyone. Good morning international jury. We are the SKUBA team from Kasetsart University, Thailand, and we participate in the SSPL League using the Peppers robot to participate in the RoboCup. At first, we just think that the Pepper is not a movable tablet like many people think that it's true. But for today's demonstration, we will be show that the peppers carrying the belonging luggage from the operators. They can detect the ingredients, detect the things that the operators do. Sorry, and the space recognition, and the last one is for the navigation. For the demonstration story, this is the first thing. The peppers will be ask the people when they come back from the shopping or the grocery store, and they see the luggage, and okay, it looks so heavy, and the peppers will be help the people, like I will be put the luggage on the table, and after that, pepper will be help the people to preparing some food. For the hearing and understanding, like the speech to text and text to speech, for the defaults in the Peppers API is might be good, but it's not enough for the RoboCup because the noise is so much. We decided to use the whisper from the OpenAI to help us to solve this problem. And after that, when we try to understand something like in the GPSR task, we use the RASA for the NLU, the Natural Language Understanding, to extract the command like give me a fish sauce, and it can encode decoding from this one into the this one, like you can see, is find and take and give to the users. And for the computer vision, we try to, because the Peppers cameras the resolution is low, and we try to extend things like extend the database of the, the dataset of the computer vision system, and we use the data synthetic generator to generate the data from the data that we get and train it into the YOLO V8. And for now, peppers will be ready and the demonstration will be shown. Okay, for now the jury, you can see the peppers from the kitchen. Excuse me, please come into this room. Okay, thank you very much. Okay, I will try to hold the microphone at the robot. Okay, for now the robot try to go to the kitchen, sorry. Due to the noise from the pepper sensors, it can use for the localization, but we try to reduce that noise. We try to fuse so many sensors as possible that the pepper have to solve the navigation problem. And for now, it try to pass through the door. Okay, for now, the peppers made some the security from the default system, but the UNG, the peppers API, they have some API for allows us to unlock the security from passing some narrow space that the pepper sensors can see. But for the real, the space is enough to pass, but the security is not allowed. We can use the API to pass it. Okay, you will be seeing it's so slow because the connection of the peppers with the robot and the API of reading some sensors is very slow for us to use in the high speed as you can see in the OPL League or others. For now, it tries to relocalize itself. And find the pathway to go to the table.
From my hand.
We simulate to change the bag because the bag is very heavy for the peppers.
Any things I can help with?
Get from the shopping.
It takes some time to process it.
I am detecting used new items. Finish detection. What do you want to eat today? Please talk to me loudly after beep sound.
I want to eat Thai food. Maybe Tom Yam Goong.
He asked Pepper with he need to have the Thai food for dinner. Might be the Tom Yam Goong. That is the favorite dish for in Thai.
After beep sound.
it shows the Tom Yum Goong pictures on the screen and asks that that is the menu that the user want to have.
Is there anything I can help with?
Sauce.
For now, he asked the peppers that is the correct ingredient for the Thai food because I think another country people cannot recognize the ingredient for Thai. Come up. Okay. Okay. You can see. Okay, Jerry, pass the demo and to the screen after this. Okay. After you see the demos, we have the things that to present you. This is what's next after this. We try to integrate the virtual slam with the peppers. We have so many research paper with these things like a virtual slam. For the first one, we try to find which room the pepper is with the object detection, and it will be guess that which room is this, and due to the network, they have some the ORB, and the last one is for the early action prediction. Okay, thank you very much.
Okay, and we'll be moving on to a quick 5-minute Q&A session.
Well, I have a question about the things that Pepper were doing. What was the story that we were trying to tell at the table?
At the table, the peppers try to tell the user for the recipe, and after that, the user is not sure about the recipe. They can ask the peppers that this is the correct recipe for cooking this menu. And after that, the peppers can tell that this is wrong or correct. But if wrong, they can show another component like the right one. And we have another show after this, like the peppers can detect the boiling water, like detect the smoke, and detect some color from the food, like when it cooked, like a shrimp in the Tom Yum Goong, because Tom Yum Goong they have the shrimp in the soup, in the spicy soup, and it can help the people to monitor the boiling water with the shrimp, and when the shrimp is cooked, the peppers can tell the people after that.
So did it succeed just now? Did the whole story succeed just now, or did it fail?
It's time up for now. Okay, I'm so sorry. Okay, thank you for your question.
So I know from experience that localization in this environment is quite challenging on the pepper because of the limited range of the sensors. I think you started talking about using the camera for localization on the pepper. Can you maybe give a few more details? What steps you took to make sure that Pepper is able to localize in the arena properly?
Okay. Can I change the slides for? No. Okay. We try to use the visual slam, like the object detection, to help the peppers that they can find the rough location of itself, like they take the sofa, they take the chair at this table. It means they are in the living room, but it's the rough. After that, we use some 3D camera with the radar to try to find the things. But the 3D LiDAR of the peppers, they have the maximum length around 3 meters. If this room is very big, like from here to over there, is more than. We try to use the ORB slam. That is use only the mono camera image, the image from only the RGB camera, normal camera, to find the location. Like we have the map in the on the ORB slam. We have the map on the 3D slam, and we have the map for the LiDAR slam. And we fuse everything together by the EKF, the extended command filters, to predict that this one might be like over there, and another will be guests, and if the location is correct, they will be trust one of them or two of them to fuse to find the right position. Thank you for your question. Anyone have a question?
Hi, I'm wondering how much of this was running on paper and how much was running on your computer?
Okay, thank you for the question. For this question, everything run on the computer because they need a high performance to solve this problem. They need the GPU to solve the image processing terms, and for the navigation, they need the CPU more than 2 or 3 CPU because they run on the parallel to localized by the AMCL, the particle filters.
Following up on that question, was anything running in the cloud?
No, everything run in locally on that computer only, and the computer connect with the Ethernet cable directly to the papers. They they not require any external device to connect the Ethernet.
So you had created a map of this area before? How long does that take?
Okay, it takes very long time to correct the map because we need to correct the map with each sensor, like the camera sensors, the 3D sensors. They need a time to fuse. When we run everything parallel, our computer cannot process, and we need to separately run it itself. Like we have some ground truth, like we measure every single wall in this map, and we try to put the papers and measure it. Okay, thank you for the question.
Thank you. Okay. Up next is Team SinfonIA from Colombia. This is Team SinfonIA from Colombia.
Like this? Ah, yeah, okay. Okay. So, hello everyone. We are SinfonIA, Uniandes. We come from Colombia and we are based in University of the Andes, Universidad de los Andes. We are undergrad students and we come here to present to you our task. So our robot will implement some research from our latest innovations, which are based off of a paper that one of our members published in the IEEE. The paper is about integrating LLMs and multimodal models into the robot's capabilities. So the robot can generate code real time to solve tasks that the person asks him, and the robot can also, using whisper speech recognition, establish a conversation with the person talking to him. For this, and to make the LLM's job easier, we implemented what is called an interface about the robot's capabilities. So all the robot's functions were abstracted to a level that the LLM can understand clearly and implementing code with a lot of precision and accuracy. We also tested different LLMs to search which one was better for each task and for AI, for speech recognition, sorry. So the robot can assist customers personally, and the idea of this task is to showcase the robot's ability to suggest decision-making and alternatives in a real-time context. Also, there's active interaction with people who have any disability, because the robot can make suggestions. So now we are going to start the task, and well, the task is about a robot who serves as a server in a restaurant in Amsterdam. The restaurant serves sandwiches, and the idea is that the sandwich order is personalized. That means that the robot takes into account the customer's preferences to take the order, and then the robot helps the chef prepare it, right? So you will be our volunteer, all right. So the robot will take your order here in the office. He will ask you some questions about the ingredients, and you can answer any way you like, but a recommendation, choose the items on the menu. You can also skip ingredients, like if you don't want vegetables or something, that's also possible. So thank you.
Hi. I had a question. Does this work?
It does work?
Yo. I had a question. Was there anything in your demo you didn't get to show us yet? Was there any sequence in the demo we didn't get to see yet? Like, would it navigate or something? What Pepper was saying, was that coming from OpenAI's models? Okay, because the patterns were all very fixed, all very similar. It was always saying the same thing. Okay, thank you.
While Pepper was speaking, it was moving its hands. And when it said, please speak loudly, it gestured to its mouth. Was that programmed like a hard-coded thing to a prompt when it says speaking, or how was that?
So the robot is still like giving a signal when I can start talking. How necessary is this still, and are you working on just being able to understand the person from the start? Because always worth just waiting for the eyes to turn blue, right? Are you taking any steps on working on improving that? Close.
I want to ask a little bit more about the demo that we haven't seen. So I see on the story that it shows Pepper will follow the person, right? In the navigation part, which we're going to see is the Pepper following the person, right? So can you just explain a little bit how that was done and what work done to make that true? Yeah, in the demo that we haven't seen, which Pepper was supposed to follow a person, can you explain the work that was done? How was it achieved, and what's the work that you've made differently from the other teams?
introduce the SSPL Final. So now we're going to the next arena. We're going to the next arena for the OPL Final.
Okay, so in 5 minutes the OPL at Home finals will start. There you can see 3 qualified teams. The first is Team Tidyboy, which was ranked 3rd currently. The SocRob team currently ranked 2nd, and the NimbRo team currently ranked 1st.
Dames en heren, zo dadelijk beginnen wij hier bij de at-home arena's met onze finales voor de Open Platform Leagues. Deze teams hebben zelf hun robot samengesteld en zullen dadelijk aan ons allemaal en aan onze vakjury laten zien wat zij allemaal kunnen om iemand te helpen bij het voorbereiden van een maaltijd. Er staan hier 3 teams in de finale. Het gaat nog nek aan nek. Dus voor deze teams komt het erop neer hoe goed zij kunnen presteren in deze komende 10 minuten.
We're just setting up for the OPL challenge. The OPL is the Open Platform League for RoboCup at Home. We just witnessed the SSPL Social Standard Platform League, where everyone was using the Pepper from SoftBank Robotics, now from the United Robotics Group. We have the same external jury: Akels Chen, co-founder of Unitree; Chayu Li, sales director from Booster Robotics; and Emil Kruger from United Robotics Group. The first team up is Tidyboy from South Korea. The teams will have just like the other finals, 10 minutes to present, do their demonstration, and then 5 minutes of question and answers. Johannes. And, yep.
Hello, we are Team Tidyboy. And we will show you today a very fraction of our mobile mainframe capabilities. Yeah, here are two of our robots. This one is Lucio, we use for the competition, and that one is called Crow, because it's dressed in all black. And yeah. Yeah, you can see our robot very promptly approach the target position and detect the item and picks up it. Another robot goes to the kitchen counter to grab the cornflakes. And now the robot goes to the kitchen cabinet where the milk is supposed to be. Yeah. Robot approaches the kitchen cabinet and sees that the right door is closed and opens it. Okay, so you can see there's another robot over there waiting. So I asked the robot to grab something from there. That's it. We can clean and rinse and leave it.
I've seen a lot of localization done in this work. Was it like done through the LiDAR down beneath, or did you use vision with it?
For the robot is actually fairly minimal, so we have the LiDAR, 2D LiDAR, and one RGB depth camera on it. So it uses both the sensors to make a setting map and dynamic map, and also some dynamic obstacle map to navigate around this area.
So you show the robot detecting the objects on your screen, which is very nice. So it looks to be adaptive to the object position. Is it possible? Are you working on if the furniture moves a lot? So right, if I do this, is it still working? And are you working on it making it possible?
Right now it's like partially working. So we go to some position based waypoint, and then check the front distance, and then approach the fixed distance from this table. So it's like kind of partially working, but for the cleaner table test, we have absolutely no idea where the dishes are. We have to manually check every location. So we'll hopefully get things better next week. Yeah.
Okay, when the robot on to pull the milk, I think it's outside the bowl. So do you know the reason?
I see. So right now, one of the main shortcoming of our robot configuration is that the camera is mounted here. So when we're holding something without springing, we use the previous knowledge of the power location, because we already put that on the table, and that knowledge to precisely align this thing. But if the power moved a bit during the meeting, we may not be precisely aiming.
Are you thinking about finding a solution to this, like adding a camera or something?
Yeah, this year we had a lot of issues with navigating through very tight environment. So we will definitely add more like sensors like 3D radar and actually a full head with articulated neck for next year.
You showed good navigation and obstacle avoidance with the other referee, but when you placed the object, you did whole body control. You moved the base and the arm towards the table. Was any of that dynamic, or was it going to a hard-coded position?
Yeah, it's sort of like it's not whole body control. It's like partially coded, but it's parameterized, so we can use the knowledge to modify it a little bit.
But there is no obstacle avoidance of that arm motion when it's going to that placement position, because you mentioned there's no camera there.
So we use a bunch of tricks to make the limited hardware configuration work. Right. Any more questions?
I was mostly curious about how well it would have worked if the items were in different places. Like, did it localize the item or just know where they were?
I think unfortunately right now we need like rough position of each waypoint. Right? The robot should know like where roughly the table is.
So if the spoon is here instead, does that work? Okay. Yeah, I see. Okay, thank you so much, Team Tidyboy.
Up next is Team SocRob from Portugal.
Hello.
Ah, what a wonderful evening. Tonight I'm gonna have a special idea for my precious girlfriend Patricia. She is from Portugal, so I thought I'm gonna prepare her something very special. I'm gonna cook some pastéis de nata. What do I need? I think I need some eggs and... I think I forgot it. Okay, Bob, tell me the recipe for the pastéis de nata.
To execute your command, I will execute the following actions. Say the recipe. Enter the task. Is this correct?
Okay, Bob, yes.
Is this correct?
Okay, Bob, yes.
Executing your command. To make a pastel de nata, you need to mix milk, sugar, flour and eggs, put it in puff pastry and give it lots of love.
Ah, now I remember. Very good. But I think I'm missing one ingredient. Okay, Bob, get the milk from... Okay, Bob.
Following actions. Find the milk. Grab it. Enter the task. Is this correct?
Okay, Bob, yes.
Alright, so in case you missed it, the Robin is preparing some Portuguese bakery, which is called pastel de nata. And so he was cooking it and he realized that he was missing the milk. And so he actually asked nobody to put the recipe for pastel de nata. And he realized that he was missing milk. So he asked me what he got the milk so he can finish the recipe for the pastel de nata. Okay? So the robot will start by navigating to the top, it will proceed to the left, and eventually pick up the milk and hand it back to Rob. So now the milk.
She's here at the dinner table. I will attempt to pick the milk at the dinner table.
So now moving to the pre-rise position. Adjusting this position so you can pick up the object. Now we'll attempt to rest it. Alright, seems to be. Successful predicting so far so good. Alright, maybe we'll have some stuff to catch up.
Thank you, Bob. Okay, finally I have all the ingredients ready and I already cooked the pastel de nata, so it's time to call my beautiful girlfriend to dinner. Okay, Bob, guide Patricia from the living room to the kitchen.
To execute your command, I will execute the following actions. Find Patricia in the living room. Guide them to the kitchen. Enter the task. Is this correct?
Okay, Bob, yes.
Executing your command.
Alright, so in case you missed it, the way we do the generic purpose search is we give instructions to the robot, your speech. Your speech is recorded and break it down into text, which is sent to the ChatGPT-like model, where this algorithm gives a sequence of actions that will just execute the function. So, for instance, in the first task, we want it to navigate to the table, to see the object, pick the object, and to give the object a run.
I could not complete the task. I am sorry.
Okay, Bob. Guide Patricia from the living room to the dining table, to the dinner room.
To execute your command, I will execute the following actions. Find Patricia in the living room.
Okay, Bob. Yes.
I was able to find Patricia in the living room. Please follow me to the kitchen.
Yeah, so we're doing visual serving as you said. So we do move it for the pre-grass position, and then we do visual serving to pick up the object, yes.
Can you talk a bit about, so we place the milk there already. Is it possible for the milk to be at a different place on the table? And is it also possible for the milk to be at a different location?
Yeah, it is possible to have the milk in a different location. So if, for instance, if we told the robot to look for the milk in the kitchen and pick it up, it would probably search all over the kitchen for the object. But what would make it hard for us is if you move the table out of place, like too much, then it would be hard for the robot because we know more or less where the table is expected to be, and if we kind of switch it around with the cabinet, then we're not responsible. Yeah, so whenever he's a known person, he just saves the photo, especially whenever it's inside, like in the map space, or in this case in the house. So it detects the person. If the person is inside the house, it takes a photo. So it should have worked at the first. I don't know what was the failure case, probably have to look into it. But that's how we do it. So the robot would approach him, and since he doesn't know him, he would take a picture. You could eventually ask his name to get a profile for him, like we do in GPSR. They keep on doing. No, it's possible. This happens in GPSR, so whenever we go beyond, whenever we start the task, we never know the people beforehand. So we always approach them, we make sure the people are in the right division, we approach them, we talk to them, we say names, the photos, every information we can about the It is definitely possible dealing with the failure scenario. In this case, he just went back to the instruction point to receive because it would just the instruction was to find Patricia in the living room and not finding Patricia in the house. So that's why I went straight back to the instruction point to receive a command. He would look in the house. So the way it works is you say okay Bob, then you give the instruction, whatever you want, and then he confirms the instruction with you. Like you want me to do this, and then you say okay Bob, yes, and then he'll tell you step by step what it will do. So we use an LLM model that is fine-tuned for this particular event, or in this case for the GPSR, which is one of the tasks of the competition, where you can take a command from a big list of commands. And so we fine-tune this version, this LLM model to this GPSR task, and then he builds, so he takes the speech command and he generates a plan, a sequence of actions based on this. It's running locally.
Thank you, Team SocRob. Up next is Team NimbRo from University of Bonn. We're just going to get a moment to get the referees and judges sorted.
Test, test, test.
All right, so we asked the referees to actually be seated there. Still, someone can also sit here. No, you can go there, and one can sit on the couch if they want. All right. So we are Team NimbRo from the University of Bonn, and basically demonstrate how these domestic service robots can get into our households, and we want to take one step towards that direction. And how we do that? We cut all the knowledge that the robots acquired during the whole week, except the maps. So we dump all our object segmentation approaches that we hardly labeled and just work with text prompts and natural language interaction. All right, so we prepare dinner. And we have a transfer task actually. So this robot is in the timeline right after this first robot. So it works with the information that it gets from the first robot actually. But as the time is limited in this final, we have to start with the manipulation beforehand. And the first robot actually scans our apartment because it does not have any prior knowledge about your objects. So the robot is going to craft the pasta, which is not an object that has been used throughout the tasks in this competition. I made a little bit of help. And the other robot in parallel scans the apartment. So imagine you just unpacked your robot and it learns your environment at home. So even the pot and the pan have not been seen before, it's just queried by language prompts. So no labeling involved at all here. There should be actually noodles falling off. So we're handling actual food, but maybe there's a block. I'd ask for a handover. But let's see, it has a second task to do. But in the meantime, we need one that wants to order something here. So maybe you just stand somewhere here and wave. So and here the robot detected a person waving, approaches him, and now receives a command which is not given in advance. It's really grammar free. He can say whatever he wants for dinner.
An unhealthy salad. So the other robot is going to grasp the egg. And again needs some support.
Hot sauce, balsamic vinegar and cooking oil. Add a sprinkle of salt and a small amount of melted butter for extra flavor. Serve the salad on a bed of pandan rice for a unique twist. Please sit down and relax while I gather the ingredients.
So and the hard task here is now to combine the natural language and ground the prompts for the open vocabulary segmentation and detection approaches. So we will grasp a complete unknown object there and try to brew an egg here. So there's actual food inside. will help it a bit. Yeah, a drop fell off. So, and the other robot, so this robot is now supposed to escape and we can focus again on this one. So this one scanned the apartment, did not have any knowledge about the objects, but is now able to pick them. So one pick failed, but the task is very hard. So it has not seen this object.
Balsamic vinegar, a white cardboard box of chocolate powder, and 2 more.
So our contribution here is to get the command that Alex gave to the robot and prepare dinner ingredients, but then we also have to ground the open vocabulary segmentation approach with these ingredients. And the objects are unknown. And still it is able to grasp them, a previously unseen object. And it now further tries to collect some details to learn what brand it is and maybe the ingredients or whatever. And it will try to grasp the second item because we recognize when we fail a grasp. No help required, unknown object. "20 seconds left. So I think it is now supposed to deliver the items, but it was a bit unfair. Yeah. All right, that's a very good question. So we have 2 robots in place, and this one was basically not our manipulation robot, so it's not really calibrated. And we focus with manipulation on the other robot, and there the robot was able to grasp also with our help and recognize when it failed and then try to achieve another object. Yeah, but obviously if this is calibrated, it should work the next time. Yeah, so all the robot knows about this object is a blue pasta box.
So on this side of the demonstration, the prompts for the open vocabulary detector were selected by us humans. But on this side of the demonstration, the prompts were selected by the vision language model which was doing the planning. So there's a slight difference on both sides, but on either side, no object was known beforehand. Nothing fine-tuned from our side.
So we did not take a single image and annotate that this is a pasta package. No,
so after the object is picked up, we do not really trust the open vocabulary detector to give us a 100% accuracy for the recovered object. So we look at it again, so we can feed those images to the vision language module in the planning side, so we can verify that these ingredients are actually the ones which are useful for the recipe. So if it had returned, it would have told you what the ingredients actually do in the recipe, because it has this information and verify it by checking these images. So this was a very deliberate, very important step. So actually the vision language model part on this side would have already been able to answer this question, but it would have taken probably, if it had gone very wrong, then it would not have been on time to prevent anything like spilling on the table, right? But not for the open vocabulary detector. I think this is still too difficult for such a model.
Yeah, but we are working towards integrating such foundational models on more and more aspects. So maybe not just on an object level, but on an object part level where we can distinguish the handle or maybe the dishwasher handle and stuff. And then obviously the next task will also translate or develop prompts for movements of the robot so that we can basically close the loop at some point and get rid of all the knowledge that the robot has in advance, including the map.
We can do this already, but the problem is that the workspace in front of the robot is actually very small. So the likelihood that two objects are at the same time in an acceptable region of the workspace is very low, and an alignment to do this is extremely difficult. Yeah, we can already do that, but we rarely do, because there's rarely a situation where it's the true cognitive robot, yes, we're working towards it.
So in about 5 minutes, the home final for the DSPL league is starting here. So there we have 3 teams competing. So we are starting with the third ranked Tidyboy. Then we will continue with the regular team, and then we have to be Hibikino-Musashi. So in 5 minutes, the home final here in the domestic standard platform will be started.
And we are ready to start the finals for DSPL, the Domestic Standard Platform League. Again, teams are going to have 10 minutes to present their work, followed by 5 minutes of questions from experts in robotics and from the executive committee here at home. And this is up first is Tidyboy from South Korea.
Okay, so what I basically try to do is make the robot serve some cereal meals for a hungry customer, who is basically me. Just a second for setting up this arena for the experiment. So from now on, I'll tell this HSR robot to tell me to go and set up my breakfast. Let me call it. Tidy boy, come here. And they would move right in front of me. Hello? Go to the kitchen and fix me breakfast. And the robot would assemble my supplies one by one. But
just to make things a little bit more challenging, I'll try to give the robot an opportunity to open the door itself and get out the cereals and milk. Okay, so the robot is looking on the dishwasher to find the bowl. So it reaches, found the bowl, and goes to catch it. Now it will move it to the dinner table. So we will be setting up on this table with one object at once, starting from the bowl, and it would attempt to pour in the cereals, then milk, then it will bring me finally the spoon. Let's see how it goes. Okay, things like this sometimes happen. Now let's see if the robot could open up the door and find itself its cereals and bring it to me. Okay, looks like it's going good. And it succeeded in opening the right shelf door. Now let's see if it could find the food and serve it to me. Okay, searching. And it found it. Let's see if it could grab it. Okay, it wasn't easy. Okay, now the robot is supposed to attempt to pour the cereal into the bowl, but since it is not grabbing it correctly, I don't think it will work properly. Okay, so this robot is currently imagining itself holding the cereal properly and attempting to pour it. And it should place it right next to the bowl. And looks like it's now going for the milk. So it's going to search for the milk. Okay, it found the milk. Now let's see if it could catch it. Okay, it's reaching too high. Did it make it? I think the robot is feeling a bit down since it went through a long days in the competitions. And yet again, the robot is attempting to place an invisible milk inside its hand. Okay. I'll stop it right here. So, Team Tidyboy, thanks. So it does know what objects to bring, but like when I said, please set me up my breakfast, it does know it has to bring its bowl and its cereal, milk, spoon. But the positions are slightly predefined. But when it reaches to the position, then it finds its vision module and finds the position where it is and reaches for it. But well, for the bowl, it worked out well. I don't think it really correctly figured out the height. It's kind of dark inside there, so the shelf inside is really dark, and it couldn't find the position of it. So I think it reached to different locations. Well, for now, yes. So I just assumed that people would put their bowls on the dishwasher. Excuse me? Yes. Ah, yes. Well, so actually there is some things that could check its failures. Such like you could see if the object he was supposed to grab is gone on the table, or you could see whether its hand is actually holding it by like the force of the grippers. So we actually did make up a backup plan for it, but we didn't have enough time to just make it up to the final scenarios. So, well, I think we would do much better next time. Yes? So basically the problem with dropping the bowl is it detects the table at real time with the RGB sensor, and it goes in front to reach for the place. But the problem was the position of the table wasn't placed aligned to the robot itself's LiDAR map. So the vision said I should go this way, and I should go like 80 centimeters. But the obvious map says, oh, you can't go there because there is something blocking there. So it wasn't able to reach there. So it just basically failed its navigation and dropped it. Yes. Yes, so it does distance the table with its vision, but like, it didn't work out with its like LiDAR system. Okay, thank you very much.
Up next is Team Erasers from Japan. They are currently in... Okay. Okay, start.
Hi, we are Team Erasers from Tamagawa University, Tokyo, Japan, and we are now distributing the handout. Please watch out the handout before the setting. Then we also need to use the round table, so please. Sorry. Okay. So, the main target of our team is how to deal with a novel environment and a personalized environment. Personalized means this is a novel environment for ourselves because we are Japanese. Then how to deal with such a novel environment. Additionally, not customized, a personalized environment, localized environment. Like how to deal with house rule, okay? Then our approach is, of course, the ideal approach is the perfect autonomous ability. That is the ideal. But we don't think that is the realistic approach because we have to deal with so many difficulties in the real environment. So our approach is to use the cyberspace to share the cognitive model, how the robot perceives and how the human or operator think and instruct to the robot. To realize such a shared cognitive world model, we realize that virtual reality and digital twin technologies to share such a cognitive model. Okay, so then this room is in Tokyo. This is the scenario. We are now Tokyo, and he is the operator to support the HSR robot. And there is not Tokyo, Eindhoven, Netherlands. Then he is an operator to support the HSR working in here, Eindhoven. But he is working in Tokyo, right? Then shared cognitive model is interact between real HSL and the virtual reality system here. This is our scenario, okay? Then, is it okay to start? Okay. The first challenge is that he is now preparing dinner, and he asked the robot to bring a snack. He needs a snack. Then HSL is now looking for the snack. The snack is here, right? But this is one of the challenges for the robot because this is localized snack, Japanese snack. So there is no information, no knowledge in the HSR database. So the robot have to learn what is the snack in this localized environment. This is a current challenge. Okay, now the robot finding something, but fortunately, this time the robot can recognize that the new snack, but we can cope with the novel environment, novel situation. If the robot cannot recognize a novel snack, Japanese snack, in that case, the operator can teach what is the Japanese snack, what is the novel snack. But fortunately, the robot is now succeeded to recognize the snack. Okay, but this was the scenario number 1. Sorry, that a bit very difficult to hear. But his instruction was he needed to grasp the Robin. His instruction was please bring Robin. Robin is the name of this doll. But this is another localized and personalized keyword. Because so many people doesn't know the name of the doll is Robin. I just recognize this is Robin when I come here. Then the robot is now faced to a trouble because the Robin is the name of the person. But he instructs the robot that please bring the Robin. But the robot cannot understand Robin is a person. How to grasp the Robin person? Then he asked the support in the Tokyo Support Center, and this is a virtual reality system that is shared the cognitive model of the current HSR model. Then the supporter pointing out, Robin is not person, Robin is a doll, name of the doll. Then the robot can understand, okay, I understand Robin is not person, Robin is a doll. Then his instruction is reflected to the real robot, and robot is now grasping the Robin. You can come here to watch the grasping behavior. The next challenge is the
So I'm very busy to make the dishes, so please set up the apple.
The next instruction of this user is to grasp the apple. You can see the apple is under the table, but this is the belief of the current robot. The apple is on the table, right? Then the robot cognitive model and the real situation is different. The gap is exists. Then robot should find the apple on the table because his belief is that apple is on the table. Then some difficulty happen to the robots. The robot recognized there is no apple on the table. So what happened? Then he asked the supporter who is working on the Tokyo. Then he pointed the, I think the alternative destination of the apple is under the table. He is one of the knowledge distributor. Then the robot is now try to check the underneath the table. But unfortunately, something physical contact is happened. 30 seconds, okay. So this is one of the several examples how to share the cognitive world model using the virtual reality and how to realize the remote supporting. And this is one of the novel technologies of our team Erasers. And we are now trying to realize the at-home simulation of the HR Lion competition using that virtual reality system. Thanks for your attention. Localization. The real performance problem. So I think the location of the table, we made a map using the SLAM, but the preparation time is limited, so the map is not the perfect. Then that is one of the reasons why the robot collide with the table. Yeah. Hi. I see. So, recent technique like a GPT and the visual foundation model, almost all the snack can be recognized by the computer vision and robots. So, if the novel snack, Japanese and Korean or Chinese or so many unknown objects are here, the robot can also recognize this is unknown object, unknown object, unknown object. So, for each object, the robot asks to the operator, please give me some additional information. Then this is some collaboration between the supporter and the robots. Hi. Hi. Direction, appearance of the snack. That is very important, a good question. If the snack. The typical appearance, for example, we can, this is one of the product, then this kind of image and appearance, the robot can access to the internet. Then some image like this is a Japanese snack, this is available. But in our challenge, the appearance and the direction is here. Then that is one of the difficulties robot cannot understand. Or this is novel, unknown product. Then our original solution was using my smartphone to take a movie from the all over the around direction. Then such a movie was sent to the robots. Then robot can recognize, this is the different direction of this object. This is that was our original scenario. But unfortunately, that was failed. So that is another difficulty is to realize the digital twin systems, because in our current challenge, the table location, like this round table, white table, were prepared in advance of the performance. But for example, apple is under the table or Robin doll is on the table. If such a current situation is not reflected to the virtual space, the robots always recognize, always observe the information, environment, and real time the environment information was sent to the virtual space. But that is one of the functions of digital twin system. So that is ongoing our research activities. And one of the basic approach is to take a map like a slum environment. And additional ongoing project is to scanning the object by smartphone or LCD camera of the robots. Then, but it is not the perfect technology to identify the location of the object, furniture, and so on. So that is our current challenge. Hi. Thank you.
Hi, welcome to our demonstration. We are Hibikino-Musashi at home. So we will show you a demonstration to help the dinner preparation. So let's see the robot over there. This is the entrance of this hall. The robot is coming to following the person. This robot is trying to follow the person. And this person have a heavy luggage. And the robot is now following the person and with a luggage. And inside of it, we have some snacks that human purchased. Now the robot reached to the destination and stop following the person and give it to the bag to the human. And simultaneously, this robot is watching this behavior of humans and the robots and observing the human put some snacks over here. So now let's see the next demonstration. It's the helping the person preparing for the dinner. So here is Soma. He is preparing for the dinner, and now he has some knife or pans and very busy to prepare for the meal. And this robot is trying to help the person who needs request. So this is some gesture to identify the person in the room. And now robot finds the person in the room and trying to reach to the person who is waving the hand.
Silla, what should I do?
Great screen with a mayonnaise and a can next to it.
Yeah, now the robot understands the human spoken command, and it was please bring me a mayonnaise and the object next to it. So the robot is trying to move to the counter because the robot knows the food items can be found on the kitchen counter. And in this system, we have a command parser system. So the natural language will be processed and plan a task by the robot autonomously. And now the robot is trying to recognize an object on a kitchen counter and try to grasp it. Of course, of course. Please go here. And robot will hand over this mayonnaise to the person who asked a request. And because this robot has only one arm, so the robot will trying to go to the shelf counter again and pick up the next item. And the next item is a can next to mayonnaise. And our system can understand spatial relationships with objects. So we give some object information to the command parser, and the robot knows this can is next to mayonnaise. So the robot is trying to grasp this can, not this can. And in this situation, the robot knows where the object is. However, in a real home environment, this object is, the information is not provided beforehand. So the robot has to know the location autonomously through the experience of the robot. So we will demonstrate. So now robot fails to identify the object. So move on to the next. So please see this slide. So as we explained, the robot has to know about their home autonomously, and such home environment or such information includes privacy information. So we have to protect it, not just sending cloud computing or something. It's better to compute in a robot edge device. So we think edge computing is very important. And in addition, the power consumption is also a problem with the robot, because the battery is very limited. So we need to charge the robot every time. So we need a low power consumption system. And here we focus on the hippocampus function of our brain, and this hippocampus handles a spatial information with a time and location information. So the robot was actually observed the situation. The human put some object here, and the robot will memorize such location of the object, for example, to the hippocampus model. And we also implement this model to a chip. And this is a chip. It's like CPU in a computer, but this is a dedicated chip for this hippocampus model. And this is ultra low power consumption. So it's very suitable for the robot to implement for more working time. So the robot is now trying to find the next person who requires help. And now Mr. Tanaka is trying to call the robot by waving their hand. And he will request to the robot.
Hi, Tanaka, what What should I do?
Bring me some snack.
So the robot will try to grasp candy on this table. And for hand wave detection, we use reservoir computing. It's a lightweight computation model for time series information. And we use in a restaurant task or GPSL task to identify the person who is waving a hand. And the training is very lightweight, and also we can implement to low power consumption device such as FPGA. So, and yeah, this is a detection of a human. And here is our summary. We demonstrate a GPSL system and calorimetric system of our robot. And in the future, thank you very much. Yes, in our team, we designed this chip or FPGA. So we have different approach to implement the model. We have suitable approach to implement it.
Can you give an example of what you can use the chip for?
Okay. So this chip can be used to memorize the location of the object. For example, here. So in the chip, the location is encoded in this two-dimensional map, and the chip knows where the object is. So by reading such object location, we can know where the object is. And this information also has some exotic memory, such as time or food, eat something, or etc.
Like now, we'll try and take a picture of what happened, and then half an hour later, remember the call and remember seeing the happened.
Yes, exactly. Or more week before or a year before. Of course, this model itself is very lightweight, so we can of course decrease the power consumption just implementing to the computer. However, dedicated chip or this kind of digital circuit is much power efficient, so we can reduce bunch of the power consumption of the robot, and we hope it can contribute to the long working hour of the robot, because current robot is only works 30 minutes or so, so this is a problem to working in a home environment. Yes, we have benchmark. Unfortunately, we have no slide, but it's like 100 much efficient than comparing to another NimbRo chip, such as neuromorphic chip. Of course. Yeah, we published a paper, so if they can implement it.
Can you talk a bit about overlapping objects?
Oh, I need to check the robot, the log actually. However, sometimes it happens. So currently we use a language model to detect an object here. So not like your system. Sometimes the system will output different things. So that is sometimes weak point of this system. However, we can tune the model by giving a prompt in a natural language. So it's more flexible to detect objects. So this is a worst case, I think.
So it's possible for me to take an outside software and go like this.
Yes. So yeah, here we need some label to identify next locality. So we need object information. Thank you very much.